Today we'll be using Doppler ultrasound in order to measure blood velocity to help determine blood flow. In order to measure blood velocity, the participant will first extend their arm 90 degrees at heart level. Next, we have to change the probe on the Doppler ultrasound to be 4 megahertz to match the 4 megahertz probe that we are using today. Once we have changed the probe to 4 megahertz, we then want to change the scale by changing the offset to be negative 32 at the bottom and 128 at the top, allowing the graph to run through 0. We then want to change the gate to 10 millimeters. Once the gate has been changed to 10 millimeters, we want to change the depth to 2 centimeters.
Changing the depth changes how deep the signal goes into the tissue, while changing the gate changes the window of sensitivity that the probe has for picking up a signal.
To start the ultrasound process, once our screen is set up correctly, we take our 4 megahertz probe and attach this homemade device, which we call a donut, to the side of the probe, allowing the 4 megahertz to be facing up. Once attached, we cover the exposed part of the probe with the aquasonic gel to start the ultrasound. Finding the brachial artery takes a lot of practice. However, the best way I found to do it is to place a probe where we believe the brachial artery would be, and then move the probe around until we find the strongest signal. When we place the probe down to find the brachial artery, it is important to realize that there are many factors that can influence the strength of the signal seen on the graph.
One of these factors is noise. This graph shows how noise can interfere with the blood velocity signal. If the wire moves around too much, there can be a lot of noise, causing a weaker and less clear signal to be seen. This can be fixed by taping down the wire to reduce movement, as shown in the picture. This produces a much clearer image, allowing us to have a better reading of blood velocity. Veins can also interrupt the blood velocity signal. Vein interference is represented by negative values on the graph. Veins produce a negative reading and make the true arterial blood velocity appear lower than what it should be.
To expose a vein that may not be able to be seen at rest on the graph, the participant will then squeeze a ball to ensure that there are no veins that may interfere with the signal during data collection. Squeeze for me, Chris. And release. Having a negative value on the graph indicates that there is a vein in the way. Once we have found the location in which we think we will get a correct blood velocity reading, we then want to change the gate, and then the depth, and then the gate. We first want to change the gate so we can barely see the signal, which usually requires to go in the negative direction. Once we can barely see the signal, we then change the depth in both the positive and the negative direction to the two extremes where the graph can no longer be seen. We take this number from the two extremes and find the average, and that is the number we use for the depth during collection. We then take the gate back to 10. Then, the participant will squeeze the ball a few more times to ensure that we are in the correct location. We mark the probe in order to ensure that we use the same location every single time. Once marked, we remove the probe, wipe down the gel, take off the sticker on the other side of the probe, and then reapply the gel for data collection. We can tape down the probe and start collection. In addition, if the participant has squeezed the ball and there is still vein interference, I can use my fingers to try to reduce the vein interference to produce a stronger signal. Before data collection can begin, it is important to ensure that the subject's resting velocity is below 5 centimeters per second. There are many reasons as to why their velocity could be above 5 centimeters per second, including taking the stairs on the way up to data collection, exercising prior to collection, or consuming caffeine. There are different strategies we use in this lab to reduce their blood velocity, including using ice packs on their chest or on their arms, in addition to having the participant stay quiet and having then practice some deep breathing techniques.
This is a good example of a strong blood velocity signal from the brachial artery with only minimal vein interference. This is a poor example of a blood velocity reading, as it includes noise at the beginning. The signal that is picked up is weak, and there is more vein interference indicated by the graph dipping below 0. Finally, this is a fairly good representation of the blood velocity while squeezing. This was the best signal I picked up while the participant was squeezing. The signal is strong and there is no noise. However, it could still be improved by reducing the vein interference.